Hi, and welcome to the second video in the PDF Scraper tutorial video series. So in this video, we're going to look at importing the PDF markups that we created in the last video into PDF Scraper. So what we're looking at here is the PDF Scraper UI. And the first thing to do once we open this is we go load PDF. So this first icon up the top here. So if I click on that, I'm going to navigate to the PDF file that we created in the last video, and I'm just going to double click on that. The only extra piece of information we need to provide now is the scale of the PDF. In this case, our page scale is 1 to 100, so I'm going to leave it at the default 100. So once that loads in, you can see that it has imported on this first page, so in this first level, all of our footings. And in this case, we're looking at structure under, so we're not seeing any columns. By default, it also shows the PDF background, as you can see in here, and that's just shown as an image behind all of these live elements, which you can see here. So if I turn off that PDF background, you can see that we're left with just our pad footings in this case. It is showing you the levels that's created on the side here. So each level is associated with a page, and you can see the page number that it's been imported from and the name of the level. It also shows the RL, which is calculated from the cumulative height of each level, and the height of the level, which we can double click on and change in here should we choose. So going back to the footing level, and I'll turn on our PDF background just for some context. You can see that we can see the pad footings. So as I said before, by default, it's showing the structure under, and at footing level, we obviously have no structure under, so we can't see any columns or walls. There is an option up here. I can click show overs, and if I turn that on, you can see that we are now able to see the columns sitting on top of these pad footings, and then the core and this extra shear wall here. Generally speaking, everything in PDF Scraper works as structure under, so unless it's needed for some reason, you're best off to keep show unders on and show overs off. So if we go to level 1, for instance, we can see that these columns are shown as columns under at level 1. This ID that comes up next to the columns is the chain number. So consult the user guide for more information on what chains are, but effectively they're a stack of individual column elements. So each column element doesn't have a name in its own right, but each stack of column elements does. And by default in PDF Scraper, these column chains are given an automatic name. Should you want to, you can change that name by right-clicking on the column and going rename chain, and then you're able to put in a new name, noting that no two chains can have the same name. So for instance, I couldn't change this to C2, for instance. You see it hasn't worked. So obviously here we can see the slabs, voids in the center there, columns and walls. We can also turn on loads if we need. So area loads come up as this blue hatch, and line loads here will come up as a dotted blue line. I'll turn those off again for now. We can also look at transfers. So you can see that transfer beams will come up as a yellow line. And if we go to our transfer plate level, you can see they come up as a bluish region there. So all of these elements that we're looking at all have a series of properties associated with them. And we can access that by either right-clicking on them and selecting properties, or we can double-click on the element and it'll bring up the properties dialog box. So you can see for a slab, we're able to edit the thickness, concrete grade, and effective pre-stress, which is used for punching shear calculations. At the moment, the properties that are assigned to these elements have been imported from the PDF. And since we didn't add a lot of properties in our PDF, you'll find that all of these are the default values. If we double click on a column, for instance, you can see that there's a lot more properties associated with a column. And a lot of these are to do with column design, punching shear, transition calculations, fire ratings, that sort of thing. We'll get into that a little bit in the next video, but for this video, I really just want to focus on initial model setup and calculating the loads. So now that we're in PDF Scraper, there is the option to do some additional geometry editing. So say for instance, once you've imported it, there's a slab in the wrong place or you missed an area of slab. You can use these blue dots to drag around nodes of this slab element here. So wherever I drag that, you can see that the geometry follows, and that'll snap to give orthogonal slab edges. The other thing you might have noticed is when you select a column, you can see that a blue dot appears on that as well. So same principle there, we can use that to drag around and edit the location. Similar with walls, of course. The other thing we can do is, should we have forgotten to draw an area of slab or an area load or a line load, anything like that, we can use the draw commands up here. So I can go draw slab, I select that, and then all I need to do is draw a slab outline, and you can see that it shows you the edge dimensions there. Once I'm done, double click, and it creates a slab where we've drawn it. So as with all the other slabs, that's been created with the default slab properties. So you can see that it's 200 thick, 40 MPa concrete. But obviously you can double click on that or right click and go through the properties box and change those values as you need. Now let's get started on getting out some loads from our model. You might have noticed there are some areas here where these slabs don't quite align properly. If I turn off that PDF background, it might be a little bit more obvious, but you can see that because these, were imported via PDF markups, there's slight misalignments, which we would prefer not to have. The model may well run with these misalignments, but it's a bit cleaner if we try and do something about them. So the easiest way to deal with these is to select align slabs or snap slab vertices up here. And if I click that and let it run, you'll see that it automatically aligns the edges of these slab elements, and it'll do that for all of these slabs on every level. The other thing you can obviously do is use the geometry editing tools. So as I was saying, moving these blue dots, I can move them around and they will snap to the slab edges in here. So we can use that to snap slabs together as if we need to do it manually. And you can see that's cleaned it up on every level now. So the model's looking, a lot cleaner already. The next thing we might want to do is to connect the walls together. So the outside of our core box is obviously created from a rectangle markup. So you can see that the corners already node together very well. But this central wall here, which we created from a separate line markup, you can see doesn't quite align with the edge wall. So what we can do to rectify that is select connect walls at the top here. So if I press that, you can see that that wall now has snapped onto that external core wall. In this case, this is a fairly simple core, but this function can be used for much more complex cores. Now, the next thing we're going to look at is aligning walls and columns. We don't strictly need to do this for simple load calculations, but should you want to export the model to ETABS, it makes sense to have all of your columns aligned on the same X or Y coordinate, so on the same orthogonal plane. This means in ETABS you can bring up an elevation along those columns and view all of the columns in the same elevation. So there's a few ways we can do that. So for instance, this row of columns at the top here, say we wanted to ensure that they were aligned on the same to the same vertical alignment, i.e. they would all have the same Y coordinate. To do that, we can drag a box around those columns, unselect that slab, and I just want to go align columns, and then we can go vertically align chains. And if I click that, it's not so obvious, but those columns have now been vertically aligned, so they all share the same Y coordinate. That's the manual way to do it. So by manually selecting column chains, aligning them either horizontally or vertically, and doing that for all of the columns that you're trying to align. There's also an automatic function which we can use. So this button up here auto align all columns orthog. So it's going to try and pick orthogonal planes and snap individual column chains onto those planes. So implicitly by doing that, it's also straightening these column chains. So making sure that one column at one level aligns with that column at the next level, and so on and so forth within that column chain. So if I click that, again, not so obvious, but all of these columns have now been aligned. So all of these columns along the right edge here will now share the same X coordinate, and if that's exported into ETABS, you'll be able to bring up an elevation along those columns and view them all in that elevation. So again, not strictly necessary for the column calculation that we're going to be doing today, but if you're planning to export to ETABS, it's quite an important step. So while we're here, you might notice that there's a few columns floating out in the middle of nowhere. And the reason for that is that on our PDF markup, we've used column over markups. So we've actually dragged, say we're on level 4 now. If I go back to level 3, you can see that we've applied a column over markup to this column on the PDF markup, when in fact there's no structure over, so there doesn't need to be a column there. No issue. All we need to do is select those columns and click delete to get rid of them. And I'll just check and do the same thing on the upper levels. 3 more here. And that's everything. The other thing that we didn't include in the PDF markup, which you may have noticed, is any loading around the perimeter of the slab for facade loads. And the reason I didn't include that in the PDF markup is that we can do it more easily automatically within PDF Scraper. So I'll turn on loads just briefly. And then all we want to do is select the levels that we want to apply these facade loads to. So I'm going to drag select all of the levels 1 to 8. Obviously, we don't want to apply facade loading to the footing level. Firstly, because there's no slab at the footing level, but also because we're assuming this facade is hung. So once we've selected our levels, all we need to do is select levels, facade loads, and then we can either generate it from a line load, so a kilonewtons per meter load, or a facade weight, so that's a kPa weight per square meter of the facade. So I'm going to do a facade weight. Let's assume that it's 0.8 kPa and click OK. Now you'll see that this line load has appeared around the edge of our slabs at all the levels that we had selected. And it's set with some offset from the slab edge. You can see here it's sitting some distance inside the slab. And that's just to make sure that it's sitting on the slab during the load calculations that we're about to look at. And again, line loads, if we select that, if we double click on that, I've got the area load, try again, line load, so you can see that it's automatically given the label facade generated, and it's 2.4 kilonewtons per meter. So you can see that's the 0.8 kPa that we input multiplied by the level height, which in this case is 3 meters, which gives us 2.4 kilonewtons per meter. Now that that's done, we can move on to calculating our loads. So the first thing we need to do that is to generate the tributary areas at each level. So I'll turn off our loadings, and then I'm just going to click this button up here, which is generate tributary areas. So we let that do its thing. And you can see that it's approximated a tributary area for each of the columns and walls at this level. At this point, it's important that we look through our structure to make sure that we, as engineers, are happy with the tributary area that's been generated for each of these elements. In this case, everything looks pretty good. I don't think we need to make any modifications. I will just look at this one, for instance. You can see that we've used this trib line here, and that trib line is effectively acting as a beam spanning between those two columns there. So you can see that that beam is attracting more load up the top here between these two, these C1 and C2 columns. So actually we want to um, apply a trib line between C1 and C2 to fix these tributary areas. And I can do that by going draw trib line and adding that in. And once I've done that, all we need to do is regenerate the tributary areas on this level. So if I go levels, generate tributary areas, you can see that that fixes that right up for us. And if I turn off slabs at the top here, tributary areas become a little bit clearer. The other method we have at our disposal to edit tributary areas, which is a little bit more labor intensive, is that we can actually go edit, allow trib editing, and these movable nodes come up. And each of these nodes we can move around as we can with the blue nodes for geometry editing, and we can edit tributary areas that way. So in this case, for instance, this tributary area here, you can see starts to wrap around the side of the slab. Let's say we want to snap it to that slab corner. All we need to do is come in here, and we're just going to remove each of those nodes. And you can see that because they were shared nodes, you end up with this effect where your tributary areas for all of the adjacent columns are affected a little bit. So we need to reinstate that shape. So I'm going to turn the slabs back on just briefly. I'm going to right click on the edge of this tributary area here and go insert node. I'm going to move that node up to that corner we want to snap to. Next, I'm going to go insert node again, and I'm going to snap it to that slab edge there. And then I'm just going to do the same thing for this trib area here, and then just snap it to the node that we've created. So you can see that now the tributary area for our column C2 no longer wraps around that slab edge there, and C6 and C7 now occupy that slab edge. So again, we just want to look through each level, make sure that we're happy with the trib areas at each level, and make any adjustments, either by the use of trib lines or by editing the nodes this way. It's worth pointing out that if you're editing trib areas using these nodes, as soon as you regenerate a given level, so you can see I've moved that one out. If I go level, generate trib areas, you can see that that has regenerated and I've lost any changes that I've made to the trib nodes. So your best bet is trying to make adjustments to trib areas using trib lines instead of moving the nodes manually like this. So I'll just turn those nodes off. The next thing for us to consider is something called a shear throw. I'll just flick over to a diagram briefly and explain shear throws. So take this classic example of a linear propped cantilever type arrangement with a UDL load on it. If we were to think about the one-dimensional tributary width of the right support, then we would take the length of the cantilever plus half the length of the backspan. When in reality, if we do a static analysis on this beam, we'll see that the actual reaction on that right support is slightly larger than the width that you would expect from that tributary width that I've shown here. And the converse is true for the left support. You'll find that the reaction on that left support is slightly lower than you would expect. The way that we deal with this discrepancy in PDF Scraper is applying a factor to the tributary area at each support location. And that factor is the ratio of the tributary area at a point to the reaction that it would receive under a static loading analysis, like we're discussing here. So for a typical interior column, we might expect a shear throw factor of 1. For an edge column, it might be less than 1. And for a first interior column, we might expect a value of 1.1, 1.2. So back in Scraper, we can see the shear throw that's applicable to each column or wall by just going to a little eye icon up here. If I click that, you can see that there's a world of data that we can show for each of the elements available in PDF Scraper. So in this case, we want to look at the shear throws for columns, and we'll turn it on for walls as well. And then if I close that, the screen is updated and we can see the shear throw value for each column and wall. By default, the shear throw value is equal to 1. meaning that there's no adjustment made to the tributary area. This may be correct for some columns, but it's going to be unconservative for your first interior columns, your propped cantilever columns, ones that are naturally going to attract more load than their tributary area would suggest. In order to edit the shear throw for each of these columns, all we need to do is double click on it, go into the properties box, and you can see that that's a instance parameter that we can edit here. So for instance, let's change this one to 1.1. If I do that, click OK, you can see that the shear throw for that column there, C5, has been changed to 1.1. Now the easier way to do this is to do an automatic calculation. So we can do that by going calculate and approximate shear throws ETABS. And what that's going to do is it's going to create a ETABS model of each level of your structure, and it's going to apply a uniform thickness slab and add a point support at each column location. It's then going to apply a 1 kPa load to that slab and look at the reaction that each of those point supports gets. It's going to then compare that reaction to the tributary area, and it's going to use the ratio between those two things to calculate the shear throw. So by default, the shear throw is going to be limited to a minimum of 1, meaning that the load will never go below that of its geometric tributary area. For the most part, this is desirable because it means that we can account for some pattern loading effects. But in some cases, it could be considered overly conservative. So we can change that in the Edit Constants menu. So if we go to File, Edit Constants, we're going to go to the third tab, Shear Throw, and you can see there's an option there for the min shear throw. So by default, as I was saying, it's set to 1. We can drop that down to 0.8 or something, should we please. And that change needs to be made before the calculation of shear throws. So once I've made that change, I would go back to calculate and then approximate shear throws, ETABS. I'm not going to do it now. It'll take a bit long to run, but that's the easiest way to do it. The important thing to remember after you've approximated the shear throws via that method is that you'll need to go through and apply some engineering judgment to each of those shear throw values to ensure that it's appropriate for that particular column or wall. By default, the shear throws won't be automatically calculated for walls, and the reason for that is because their in-plane stiffness tends to attract a lot more load when doing an elastic analysis like we're doing in ETABS. So you'll find generally that the shear throw will be quite large for the walls and a bit lower for the columns around it. So the engineer should manually make an assessment of the shear throw required for the walls and cores of the structure and validate that the shear throw for each of the columns is appropriate. So at this stage, we would go through and input all of our shear throws, but for the purposes of this demonstration, I'm going to leave them all at 1 for the minute. The next thing we need to do before calculating our rundown loads is to look at those transfers that we added to the PDF. So I might just turn off these shear throws. And I'm going to turn on transfers. So I'm going to click Show Transfers at the top here. If I just flick through the levels, you can see at level 4, we come to our transfer plate. So actually what that transfer plate needs to do is it needs to take some loads from the chain over and distribute them out, a percentage of that load out to the columns under. So for this, we're going to turn on Show Overs. So if I click that, we can see that these columns on the right here have columns over, which we expect, and there's a series of columns in the middle of this transfer plate that are over and not under. So for now, we can manually input these transfers. So I'm going to double click on that transfer plate, and that brings up our transfer definition window. So what I'm going to do is I'm going to right click in there, I'm going to go add row, and then we're going to select the under column, the over column, and the percentage of the total load in that column that needs to be transferred into the column under. So I'm going to select the under column as C9, the over column as C29, and for the purposes of this, let's say 60% of the load finds its way into C9. We'll do the same thing for the column on the right. So the under column is C10, over column is C29, and let's say 40% of the load finds its way into the column under. Now I'm just going to do the same thing for those other three transfers. So we have under C14, over C30, under C15, over C30, and I'm just going to do 60-40 split again. And for the bottom one, we've got under C16, we've got over C31, if I can find it, C31, and we've got C17 under on the other side. And again, we'll just do a 60-40 split on that. And then we'll go OK. So that's the transfer plate. The last thing we need to do is take care of those transfer beams at level 6. So same thing, I've got these transfer beams here. You can see the columns over, columns under. I'm going to double click on that transfer beam. We get our transfer definition window. I'm going to right click, we'll do that twice. So we've got a column under C5, we've got a column under C6, and a column over is C32, which is there already. So let's say that 70% of the load goes to C5, and we'll send 30% of the load to C6 below, and click OK. I'm just going to do the same for this one here. So under, we've got C23 and C24, and over, we've got C33. And we'll leave it at a 50-50 split for this one, which is about right. All right, so that's our transfers completed. You'll note that I've input them manually in this instance. In a lot of cases, this is the easiest way to do it, but there is also an option to attempt to calculate them automatically using a similar method to what is used for the shear throw calculation. So to do that, you would just go calculate, approximate transfer ratios, ETABS. And all that's going to do is it's going to create an ETABS model of, say, a frame element in the case of these transfer beams, or a plate element in the case of the transfer plate. And it's going to apply point supports under that plate or beam, and it's going to apply point loads to the surface. And for each of those point loads, it's going to look at what percentage of that point load makes it to each of the reaction points. And it's going to create the transfer ratios based on that. Again, there's some constants that can be edited for transfers. And if we go to the transfer tab in here, there's a few things we can look at. So the first one is the minimum transfer ratio. So that means that an uplift will never be recorded. Or if an uplift is recorded in the ETABS analysis, it'll be ignored, and the transfer ratio, that particular transfer won't occur. You can drop that down to -1 if you like, in which case it'll pick up all of those uplift reactions. When you have a lot of columns landing on the one transfer plate, sometimes it can be a bit conservative to not allow for these uplift reactions. You'll find that you get a lot more. The load in the columns below will be much greater than it would be otherwise. There's also some rounding tolerances for the transfers. So by default, it's rounded to the nearest 5%. And if it's less than about 2% based on that ETABS calculation, it'll ignore it and take it to 0. So the last thing I'm going to look at before getting onto the load calculation is a couple of the validation functions that are built into PDF Scraper. And what these enable you to do is just validate your inputs and ensure that you can have some faith that the model is doing what you want it to be doing, and you're not losing load all over the place. So if we go validation, the first one we're going to look at is check chain continuity. I'll click that. In this case, all of our chains are continuous, so it's not an issue for us. But what that's doing is it's checking that for each chain in the structure that it exists at every level that it can. So there's no discontinuity. So if a column exists in a chain at level 1 and level 2, level 4 and level 5, it's going to tell you that's a discontinuous chain because there's no column at level 3. So just to demonstrate that point, if I turn off overs for a second, I'm going to select C6 here. I'm just going to go into that column and I'm going to assign it no chain. So I'm going to take it out of the C6 chain. Oops. And you can see that that is now indicated to be an orphan. So an orphan column is a column that's not assigned to any chain. Walls can also be orphaned. So if I run that same check now, so validation check chain continuity, you can see it tells me that column chain C6 is discontinuous at level 5. And that's because we've taken out the column at level 4. So that's expected. Discontinuous columns are errors in PDF Scraper. So if you have discontinuous columns, they must be fixed. So I'll just chuck that orphan column back into chain C6, and then everything's good. You'll see if I run that again, no errors, everything's fine. The next one we can check is the transfer totals. So I'll select that, and it's basically saying what percentage of each column being transferred makes its way to ground. In this case, we can see that we're getting 100% load transfer at each of our transfer levels, which makes sense because we put in, each time we put in our transfer manually, we've added it up to 100%. If you automatically calculate your transfer ratios via ETABS, you'll find that you probably won't get 100% for each of these transfers because obviously by default you're not assuming any uplift reactions, and also you're rounding to the nearest 5% transfer. So those rounding errors do start to add up, and you might find that you have a transfer percentage of greater than 100%. Generally, it's not an issue because obviously it's being conservative on column loads. Where it is an issue is if that transfer ratio is less than 100%, it means that you're losing some of the load being transferred out at that level. So the load in that column wouldn't be making its way to ground. So that's certainly something that would need to be checked before you go any further at this stage. The last one I'm going to look at, or the second last one I'm going to look at now, is this check founding levels option. So what that's going to do, it's going to tell you where the columns are founding. And that's untransferred columns. So columns that don't have their load transferred out, where do they end? So for the most part, you're going to find that they end at ground or your footing level. But occasionally you'll find that you've got some column load founding at an unexpected level, in which case you'd need to look into that and make sure that that load is making its way to ground. So now that we've validated our model, we've fixed any errors that occur, it's now time to do the load calculation. So to do that, we click this calculator icon up here, and that'll calculate all the loads for us. So if there were any errors that occurred during that load calculation process, it would pop up and tell us. In this case, it hasn't, which means that everything's good. So now that that load calculation is done, we can inspect the load in a column. So by right-clicking on it, I can go inspect load, and that's going to tell us the dead, live, working, and ULS load associated with that column. The other thing we can do if we want to compare various columns is we can go back up to our little eyeball, and we can turn on axial loads for that column. And we can do it for walls as well. I'll turn those on too. And you can see, again, it gives us dead, live, working, and ULS for each of those columns. And we can look at that. We can look at that at each level. So now that we've done that, we can go on to design our footings, columns, walls, now that we've got the loads, or we can simply export those loads from PDF Scraper and deal with them externally. So there's quite a few different export options. For instance, for the loads, we can do a rundown spreadsheet. There's two versions of that. I recommend using version 4. The data that comes from PDF Scraper fits into version 4 a bit nicer, whereas there may be some inconsistencies in version 3. The load will be exactly the same, but the numbers might look a bit odd. And all that is a spreadsheet that's doing the actual calculation. So that's going to input the slab thicknesses, tributary areas, all of the information from Scraper into this spreadsheet, which then in turn does this load rundown calculation, meaning that you can then change loads and tributaries in that spreadsheet, and the loads will be recalculated. The other thing we can do is just straight up dumb spreadsheet load exports. Consult the user guide for exactly what the difference between each of these is. It goes into some detail on them, but effectively you can do just the base loads of each column, a column schedule, so you get each level, all of the loads at each level, a load schedule where you have a tabulated list of the loads, and you can also group the walls into wall groups and export loads for the entire group. So a couple of other export options we have. We can export the model to an ETABS model. So if I click that, there's a few options that come up. There are it'll put the model into a template, so we can either use a ULS or an SLS template. You can select the version of ETABS that you want to use, and there's a few other options here. So by default, it won't export core walls or won't export walls, because normally there's alignment and other things you might want to do to the walls before you put them into ETABS. But if you do want them input, you can check that. By default, it won't export area loads or line loads, but again, you can add that whether you want the columns to be pin-ended or not. And the last one here, average slab thickness. So by default, it'll average the thickness of the slab at every level instead of doing regions of different slab thickness. This works very well, and you won't have any issues using this. But there is an option to get rid of that, and then you can actually it'll actually try and export the actual slab thicknesses at each point. This function is experimental at this point, and you might have some issues using this. So unless you really need it, I do recommend using average slab thicknesses for that. So I won't export that now, but that's how you would go about it. We can also export DXFs, so of the full structure, so that'll export a 3D DXF of the full structure, or just the current level as a 2D DXF format. We can also export SAFE files, so SAFE, the slab design software, you can export an F2K file that can then be imported into SAFE. We can also create new PDF markups based on our structure here. So we can either export them with a blank background, so that's going to create a blank PDF set and just add markups onto the blank PDF, or we can actually go a new background set. So for instance, if the markups were created on top of an architectural set and the architect has changed their drawings, you can actually save these markups back onto the new drawing set by selecting new background PDF set. And I'll go into these functions in a bit more in future. So I also want to touch on key plans in this video. So if we select this option here, so print key plans, this is going to enable us to export views from PDF Scraper. So what we're going to get is exactly what we're seeing in this window here on each page. So I might just change this to landscape, and you can see if I scroll down, we're getting a PDF export with all of this metadata at the top here, and it's giving us exactly what we can see in the viewer window here. So if I get out of that, turn on some random information for these columns, go back into this, you can see that now actually we're getting the updated information. So anything that's visible within our viewer window here is going to be visible within this print preview window here. And from there we can print that to either paper or we can print it to a PDF. So once we're finished with our PDF Scraper session, we've got two options for saving our information. We can either select this first option here, so save to source PDF. And what that's going to do is it's going to save all of the information, everything that we've changed in our model since importing it from the PDF. It's going to save that back to the PDF that we originally imported it from. So all of the properties that we changed will be saved back into the properties box. Any geometries that we've updated will be updated in the PDF. Tributary areas will be saved back in there. Loads will be saved back in there, noting that the loads will be deleted if the PDF is changed subsequent to that export before it's loaded back into PDF Scraper. The other option, and is generally a bit easier, is to just save something called a scrape file. So if I select that, all it's going to do is export a file called a scrape, and that's a direct import back into PDF Scraper next time we want to use it. And that's going to save all your loads, any design data, anything that you've got in the file, and makes for a much easier import later on. So that's all I want to touch on in this video. In the next video, we're going to talk about design. We'll talk about designing columns, designing walls, designing pad footings, and a few other special features of PDF Scraper. Thanks for watching this video. I hope to see you next time.